I have here a couple problems that people may consider to be slightly irritating, so I'm just going to do them. So the first one that I have that may be considered to be slightly irritating is x squared minus x plus 1 over x plus 1. The first step is to find our x and y intercepts. And already we have a nuisance sort of problem, because here this is an irreducible quadratic. If we were to put this into the quadratic formula, we would find out that it does not reduce. So if I put this into the quadratic formula, I get minus 1 plus minus square root of minus 1 squared minus 4 times 1 times 1. And we can see that in here we're going to get an imaginary number. So there are going to be no x-intercepts. And it's not really a big deal, but right away that can throw some people off because they'll just be confused by it or whatever reason. Actually, this is quite an easy problem, because there just isn't that much. So we know that there are no x-intercepts. So now let's look for y-intercepts. Y-intercepts we put in f of 0, and this gives us 0 squared minus 0 plus 1, or 0 plus 1. This is going to give us 1 over 1, which is 1. So this is the y-intercept. Oh, this is not a minus, this is an equals. Probably shouldn't have included that, but oh well. So now that we found that there are no x-intercepts and that the y-intercept is equal to 1, let's look at the vertical asymptotes. And vertical asymptote is anything that's going to make this denominator equal to 0. So we can see that minus 1 is a vertical asymptote. Vertical asymptote is at minus 1. So that was simple enough. And next we look for horizontal asymptotes, but we know that when the numerator is greater than the power of the numerator is greater than the power of the denominator, and this is 1, that there is no horizontal asymptote. However, in the special case, which is the problems that we've been looking at recently, in which we have an oblique asymptote, is where we have the power of the numerator greater than the power of the denominator by 1. So we can see that there is going to be an oblique asymptote here. And we find that oblique asymptote by just dividing out the denominator. So we can do that. In this case we can use synthetic division, because this part right down here is a first order, or a first degree polynomial. So let's do that synthetic division. So I'm just going to do minus 1, and then we have 1, minus 1, and 1. So bring down the 1. So the oblique asymptote is equal to x minus 2. So that was a simple enough problem. And now what we do is we make that table where we put all of the x-intercepts and vertical asymptotes on. But first, usually I just like to graph it, because sometimes I can save myself a little bit of work. But you can do it in whatever order you like. It's not really important. What's important is that you come up with a system that you're comfortable with to solve problems, and whatever system you come up with that works for you, that's what you do. There are a lot of different ways of going about these problems, or at least in math. So we said earlier that we had a vertical asymptote at -1. Here's -1. And then we had an oblique asymptote at y is equal to x minus 2, I believe. Yep. That's easy enough to graph. When x is equal to 0, y is equal to minus 2. When y is equal to 0, x is equal to positive 2. So this is where our oblique asymptote is going to be. And I can already tell you from the fact that we had a y-intercept at, what was it, 1? Yeah. Let's go check. Yeah, y-intercept at 1. So when x is equal to 0, y is equal to 1. So we know that this oblique asymptote, or this graph is going to come up to this vertical asymptote like that, and then it's going to come over to this oblique asymptote like this, and it's not going to cross the x-axis because we had no real zeros. So it's not going to touch the x-axis. It's going to go up like this and come down like here, and that's what the graph is going to look like. And then the other side is going to be down here somewhere. But let's do the chart anyways for people who like the chart. So this is going to be a kind of amusing situation where we're only going to have one number on our chart, and that's going to be -1. Because on our chart, what we do is we put our vertical asymptotes on, and the place where the function is equal to 0, so any x-intercepts we have. And in this case, there are no x-intercepts. So this is, in fact, going to be the only point on our little chart. And in fact, we already know one of the points, 0, because we tested the y-intercept and we found out when we put in 0, we got 1. So this is going to be on the positive side of the graph. And all we really need to do is just test some other point out here. Let's just pick -2. But like I said, we already know where this is going to be. It's going to be down here somewhere. That's just the way oblique asymptotes work. So we can just put this into our equation, x squared minus, so we had x squared minus x plus 1 over x plus 1. So we put in -2 squared minus -2 plus 1 over -2 plus 1. So this will be 4 minus -2 is 6, 7, and then this will be -1, so this is going to be equal to -7. And that doesn't fit on my graph, but it doesn't fit on my graph, but it's going to be somewhere down here. So kind of where we predicted. So here's -2, and it's going to be down here somewhere. And I'm just going to guess what it looks like. It's going to look something like this, and it's going to get closer and closer to that asymptote. Actually, that's not a very good drawing of it. So let's say, so -7 is like down here somewhere. I'm just going to say it comes in and kind of goes like this. And if you want to be super accurate, what you can do is you can test another point if you'd like. It's not really necessary for most of the time because it's just supposed to be a rough graph anyways. And here we had the y-intercept, and it's going to go something like that and get closer to that asymptote, and then it's going to come across over here and then get closer to this asymptote somewhere. And it's not going to cross the x-axis because otherwise we would have had a 0. So it's going to look something like that. Obviously this is not a very good drawing, and I can't really help that because I'm terrible at drawing. and I don't feel like spending all day testing a million points. But if you want to test more points, you can. Like I said, really the whole point of the chart is just to get a rough idea of what it looks like. We can use computers to get very, very accurate graphs. And if you really want a super, super accurate graph, you should probably use a computer instead of drawing it by hand. But anyways, this is a basic idea of what it looks like, more or less. I'm going to do one more that is a little bit annoying as well, I guess. So let's put it up. It's x cubed minus 2x squared plus 1 over x squared minus 1. And here what we need to do is use some of the knowledge we've gained from previous sections about finding zeros of polynomials in order to figure out this one. Because when we first start doing oblique asymptotes, most of the questions they're going to give us are going to be an x squared in the top and then an x to the first power in the bottom. But if they want to be a little bit more difficult or a little bit more tricky, what they're going to do is they're going to start doing higher powers. They could do an x to the fourth up here and then an x cubed down here, an x to the fifth up here, then an x to the fourth down here. And it's the same process, but it just involves a little bit more work, as we can see. Because the first thing we're going to want to do is figure out where the x-intercepts are. And here, when we have a higher order polynomial or a higher degree polynomial, we need to use the methods that we learned previously about finding the zeros of a polynomial in order to figure out what those zeros are, and that just involves a little bit extra work. Whereas in the case of a quadratic form or a quadratic equation in the top, it was easy just to use quadratic formula or look at it, and then we have a very fast way of getting the zeros. So anyways, let's just start by getting the zeros. Here it's not apparently obvious, at least to most people, what the simplified form of this is. There's usually some little tricks for something like in a form like this, but honestly I wouldn't really spend too much time learning those. So let's just use the P over Q method to figure out what the numerator's zeros are. So if we want a P over Q, that's going to be plus or minus 1 over plus and minus 1. So thankfully that's a very, very easy one. So all we have to check for are plus and minus 1. However, in this case we can't really use... Oh no, I'm sorry, never mind. I did not mean... I was thinking about the next part. But anyways, let's just figure out what the zeros of this are. We know there's going to be at least one real zero, because it's an odd polynomial. So let's just test 1 first. So we'll go over here, we'll put 1. We have 1 minus 2, and then we have a coefficient of 0 for x to the first power. We have 1. It's very important to remember that 0, otherwise this synthetic division is not going to work. Minus 1, minus 1, minus 1, 1 times minus 1 is minus 1, and 0. So this divides evenly. So positive 1 is a 0. So if I pull this out, and I'm going to be left with x squared minus x minus 1. And looking at this, I can say that there's not really a simple solution to this, not that I can think of. Two numbers that multiply to be minus 1 and add to be minus 1 as well. I really can't think of any off the top of my head. So what I'm just going to do is put this into the quadratic formula. So this is going to be equal to minus 1 plus or minus the square root of minus 1 squared minus 4 times AC, which is 1, and minus 1 over 2a to 2 times 1. So this is going to simplify into 1 plus or minus square root. This is going to become positive 4, so I didn't need to make it that long. 5 and then over 2. So it has two more real zeros of 1 plus or minus the square root of 5 divided by 2. So that's going to be a bit annoying to graph. So that's why I picked these ones. So this finally simplified into x minus 1x minus 1 minus the square root of 5 over 2 and x plus, oh no, sorry about that, getting ahead of myself, x minus 1 plus the square root of 5 over 2. So it has zeros of 1, positive 1 minus the square root of 5 over 2, and positive 1 plus the square root of 5 over 2. Now let's figure out what f of 0 is. So we can figure out what the y-intercepts are. Let me write over here really quickly too. These are x-intercepts. So for the y-intercepts we need to put in f of 0, which is going to be 0 cubed minus 2 times 0 squared plus 1 0 squared. Is it minus or plus 1? Yeah, minus 1. So all this is going to be 0, that's going to be 0, that's going to be 0, that's going to be 0, so we get plus 1 divided by minus 1 is minus 1. And this is the y-intercept. Now we need to look for vertical asymptotes. And like in previous examples I've done, what I usually like to do is leave this factored out in the top in case we have a situation where we're going to get a hole in the graph. Then it's more visible. Because that can be something you can forget real easily. And then we have x squared minus 1. X squared minus 1 is equal to, so we have all that stuff on the top. Let's put n for there now. X squared minus 1 is x plus 1 over x minus 1. And here we can see that there is a situation where we're going to have a hole in the graph. See, x minus 1 and x minus 1 cancel each other out. So actually now we can go modify this and say that there's actually no x-intercept here because this is a hole, it's undefined, so there is no value for x at 1. So these are going to be only x-intercepts now. And also there's going to be no vertical asymptote at x is equal to 1 because it's a hole. And when I graph this, it will become easier to see what is happening. So there's a vertical asymptote at only x is equal to minus 1. And there is no horizontal asymptote, but there is, however, an oblique asymptote. So let's write that out again. So we have f of x is equal to x cubed minus 2x squared plus 1 over x squared minus 1. And here we're going to be in a situation where we're not going to want to use synthetic division because we have an x squared. We have a second a second power polynomial. So we're not going to be using synthetic division. What we're going to be doing is using long division. So I have x squared minus 1, and I want to divide it into the numerator. And this is in order to figure out what the oblique asymptote is. So in order to get an x cubed, I need to multiply by x. So I'm going to get x cubed minus x. So these will cancel out. I'll bring down minus 2x squared. This will become plus x. And then we have this plus 1 down here. So in order to be equal to minus 2x squared, I need to multiply this by minus 2. Multiply minus 2 by this. Minus 2x squared plus 2. Now I'm going to be left with a positive x and a minus 1. But we don't really care about the remainder. It's not really important. All we really need to know is that we can't divide any further. X squared does not divide into x to the first. So this is our oblique asymptote up here. Y is equal to x minus 2. So now we're in a situation where we can make a graph, or a chart, I mean, and a graph too. I'm just going to put the graph right up here for right now, and then we'll come back to this. Actually, let's get our x-intercepts and our vertical asymptote. So I have a vertical asymptote at minus 1. And then we have these zeros at minus 1, at 1 minus the square root of 5 over 2, and 1 plus the square root of 5 over 2. And I don't really know what those are, so I'm going to put those in my calculator real quick. Let me see what that is. So this is about minus 0.6, and this is about 1.6. And I'm just going to estimate where these are on the graph. Obviously, I'm not going to be able to do that perfectly. So we have 3 points we need to put on the graph. So we have minus 1, and this is a vertical asymptote. We have 1 minus the square root of 5 over 2, which is about minus 0.6. And this is an x-intercept. And then we have 1 plus the square root of 5 over 2. And this is about 1.6. Let me double check that real quick. I don't want to mess up. 1.618, and then minus 0.1618. I'll take that. So here's our 3 points. So we need to test a point here, we need to test a point here, we need to test a point here, we need to test a point here. But also what we can do is take a look at the graph first and see if we can eliminate any possibilities, or just get a general idea of what it's going to look like beforehand. It's not scaled very well, but whatever. Whenever I draw something, you might want to draw it yourself, because I just suck at drawing. Oh, it's terrible. Oh well. So we had a vertical asymptote at minus 1. And then we had, what was it, y is equal to x minus 2. We had the same thing? We got the same thing twice in a row. I can't believe that happened. So we have when y is equal to 0, x is equal to positive 2. When we have x is equal to 0, y is equal to minus 2. So this is the exact same shape as the first example, which I did not intend to happen. And we had our zeros at minus 0.6, which is, let me do it in a different color. Minus 0.6, which is probably somewhere around here. And we also had a 0 at 1.6. So it's probably somewhere right around here. So we can see what this section is going to look like. It's going to look something like this. It's going to go from here up to positive infinity, up this way, and then it's going to come down here, and it's going to turn and start going along this line. And then on the other side, it's going to be down here somewhere. I mean, honestly, we probably don't even need to test points, but let's do some anyways. So let's rewrite the equation. We got x cubed minus 2x squared plus 1, x squared minus 1. So let's start with something like minus 2. So we put in minus 2. So let's put in minus 2. Actually, I'll probably do this in a different color. So I'll test minus 2. I don't really have a lot of room. But let's say I put in minus 2. Actually, I'll scroll over. So minus 2 cubed minus 2 squared plus 1 minus 2 squared minus 1. This is minus 8. This is minus 8. This is plus 1. So this is minus 15 divided by minus 3. So this is minus 15 over 4. That's 3. So this is going to be minus 5. So we have the point minus 2 minus 5. So f of minus 2 gives us minus 5. Minus 2 minus 5. So that's somewhere down here. So we can see that it's going to look something like this. And here it's not really necessary to do all this. Actually, let's look at where's our y-intercept? Our y-intercept is at minus 1. So that'll be another useful point. So here's minus 1. So yeah, here we have 3 points. So we don't really need to use the chart anymore. So it's going to get closer and closer to this line. Not actually touch the line like that just did there. So it's going to get closer and closer and closer and closer until it's practically the line. Same thing here. Now it's going to go up towards this vertical asymptote, and it's going to be close to it, but it's never going to touch. So here we're able to save a lot of work by just doing the graph beforehand, and whenever we're doing oblique asymptotes or anything really, it's helpful. Anything you want to graph, it's helpful to start with the graph and then put the information that you do know on there, because you're going to have to put it on there anyways. And every once in a while, not necessarily always, you'll be able to eliminate some of the work. Like here, we didn't really need to fill in this chart. If we want to fill in this chart, then we could have put in, I don't know, minus 4. We could have done f of minus 4 over 3 here, because this is 0.6 here, we could have done f of 0, which we did do, and here we could have done f of positive 2. We could have found out what all those different things are and then plotted the points. But we know what oblique asymptotes are. They are essentially lines, but then they behave differently when they're around vertical asymptotes. But it's essentially a line. That's basically what it is. So we can use what we know about nature of oblique asymptotes and of rational functions to save ourselves some work. So we know it's not going to go all crazy if it's a rational function when we have the numerator is 1 degree greater than the denominator. We know essentially that is basically a line, and the only places that it's going to behave not like a line is when it approaches a vertical asymptote. So we're able to save ourselves all that work.